Matrices. What are matrices? Matrices in mathematics are one of the most important objects of practical importance. In the theory of matrices, the short explanation is a matrix is a rectangular table. So you can fill out there any database you need to. All right, a rectangular table. Let me see how a rectangular table looks like. So I have A11, A12, A13, and blah blah blah, A1N. Next, A21, A22, A23, blah blah blah, A2N. Okay, well, it will continue here, blah 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 blah, and we are getting A, M1, A, M2, A, M3, blah blah blah, and we are getting A, M, N. Okay, and we call it matrix of the size M times N. M, it's what we call amount of rows. N, what we call amount of columns. Okay, so a rectangular table consisting of numbers located in M rows and N columns we call MN matrix, or simply just matrix. Okay, so in this matrix we see elements A11, A12, A13. First index shows the row, second index shows the column. So A11, first row, first column. A12, first row, second column. A13, first row, third column. A1N, first row, nth column. And the last one, first element AM1, M meaning M row and first column, and then M row, second column, mth row, third column, and mth row and nth column. Okay? AIG, if I want to refer to, let's say, element of the matrix, I can write down as AIG. Okay? Those are it. This is what we call element. So the first element means the row. I will represent the row, and J will represent the column, where I, in our case, it can be 1, 2, and all the way to M, and J, it can be 1, 2, and all the way to N. Okay. Now, a matrix is called rectangular if M is not equal N. So let's write down. If amount of rows is not equal to amount of columns, meaning M is not equal N, then we call rectangular matrix. matrix. Okay. If M is equal N, meaning amount of rows is equal to amount of columns, then we call square matrix. And the number n in the square matrix, where the number n, we call its order. Let me write down black color. Order. So in a square matrix, n is we call order. Since m is equal, so m or n doesn't matter. Next, determinant of a square matrix. First of all, determinant can be, we can work with determinant only and only if our matrix is square, which means amount of columns is equal to amount of rows. So determinant represent a scalar value, number. How to understand what means determinant? There are all kinds of definitions, but they are so complicated, so I think it's, instead of helping, it's confuse even more. So first of all, the determinant we write down like this. Okay, this is our determinant. Or you can put determinant A, doesn't matter. Either way, it's gonna work. So how to explain easily so you would understand? Like, let's say on input, you are entering some database, some table, which is matrix in this case. Okay, this is on input matrix. And the device does some determinant, do some calculation, some process, and gives you from this entire matrix, makes some sense, and give you a number. Okay, that's what determinant is. So determinant takes the matrix, that process it, and gives you the result. When do we need that? When do we use it? Why do we need this? We need it when we are using a large amount of linear equations, n amount of system of linear equations. We need in calculus, let's say we need change of volume, change of area. So in these areas we are using determinant. Okay, next. So we learned that square matrix is the matrix where amount of row and columns are the same. Okay, which means that's why it's matching square, sides are equal. Also, a square matrix is called non-singular. Let me see, non-singular if determinant is not zero. Okay, if determinant, I put this way, determinant is not equal zero, then we have non-singular matrix. Okay, if determinant is zero, Then we have special or singular. Special or singular matrix. Okay, next. Matrices are said to be equal if they have the same number of rows and columns and all corresponding elements are the same. So one more time, matrices are equal when they have the same number of rows and columns and all the corresponding elements are the same. For example, let's say we have matrix A that has the following elements: 3, -2, 1, and 4. We have matrix B that has 3, -2, 1, and 4. And we have matrix C that is equal, let's say, 3, -2. Let me make some space here. 3, -2. Let's say 5 and 4. And we have matrix that has 3, -2, 1 and 4, 6 and 3. From here we can say that A is equal B. Matrix A is equal to matrix B. Why? Same amount of columns, 2 columns, 2 rows, and elements are equal. Now, A is not equal C because although same amount of columns, same amount of rows, but not elements are equal. A is not equal to D because although it has same amount of elements, same elements on the top, 3, -2, 1, and 4, but there is additional 6 and 3, and which means also amount of rows are not equal, amount of columns are not equal. Okay. So a matrix is called zero if all of its elements are zero. So the zero matrix can be denoted by 0 or 0m times n. So 0 m times n, this is the size of matrix, m rows and n columns. Let me rewrite again. Is equal, let's say, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, or I can write down 0, 2 times 3, which is equal 2 rows and 3 columns, 1, 2, 3 columns and 2 rows. Okay. Matrix A, we mark down either A prime or AT. I'll tell you what is T. Okay, A prime or AT, which is obtained from matrix A by replacing the positions of rows and columns, we call transposed relative to the matrix A. Okay, let's say we take the columns, make it rows, and we make the rows, make it column. How we are going to do that? Okay, let me take the first one here. We have Let me see. Copy, so not to waste time. I'm going to write down, paste here. All right. So if I wanna transpose, it's gonna be equal. So AT. Look, what do I have? This first column, A11, A21, AM1, I'm going to place as a row, which means it's coming here A11, A21, dot dot dot, AM1. Okay, next, I'm taking the second column and I'm placing as a row A12, A22, dot dot dot, AM2. Next, I'm taking third one. It's gonna be A13, A23, dot dot dot, AM3. And lastly, so it's gonna be dot dot dot, we're skipping, and we are getting A1N, A2N, dot dot dot, and we are getting AMN. This is what we call transposed. Okay, transposed matrix, the related to the matrix A. All right, the operation of transition to the matrix, to the transposed matrix, is called transposition, transpositional matrix A. So for M times N matrix, the transposed, if size of this matrix is here, M times N, then size of this one is going to be N times M. Okay? Because it's going to switch here, right? Column become the row. All right. Now, what if I take transposed matrix of, I take one more transposed matrix. Look. Transpose, and I take transpose of transpose. What's going to happen? I'm getting back to our original matrix. Okay? So let me do some example of transposed matrix. Let's assume we have matrix A. We have matrix A. So first row 5, 1, 2, second row 3, 2, 1, third row 0, 2, 3. A transposed is going to be equal. So 5, 3, 0 becoming row, first row 5, 3, 0. Second column 1, 2, 2, this one becoming second row 1, 2, 2. And third one, third column become third row 2, 1, 3. So if you take another transposition, then you are going back to original matrix A. All right. Now let's move to the type of matrices. What types of matrices are there? Quite a few. But before I get to there, I would like to talk about main diagonal of a square matrix. So, the main diagonal of square matrix is an imaginary line connecting its element in which both indices are the same. Okay, let me show you. We have, or I can show you, okay, I'll go here. And it has to be the square matrix, by the way. Diagonal you can get in square matrix. So we have A11, A12, A13, A14. Okay, so I have to go 4 times. A21, A22, A23, A24, A31, A32, A33, A34, and A41, A42, A43, A44. Okay, diagonal of this matrix is going to be, see, imaginary, we're providing imaginary diagonal line, and you are getting your elements on diagonal with the same indices, 1, 1, 2, 2, 3, 3, 4, 4. Okay, so these elements that laying on imaginary diagonal line we call diagonal elements. But other elements in square matrix in which all elements outside of main diagonal elements are equal to 0, let's say I have A11, hold on, A11, 0, 0, then 0, A22, 0, 0, 0, A33. You see, we have diagonal one line, 1, 1, 2, 2, 3, and we have square matrix. And if other than elements on diagonal line, other elements are 0, then we call it as a diagonal matrix. Let me move it here so we will have it organized. Diagonal matrix, and I'll bring example. So we have, let's say, 3, 0, 0, and then 0. Here I have 4, 0, and 0, 0. Here I have 5, for example. So this is going to be our diagonal matrix. Okay. Next, scalar matrix. What is scalar matrix? A square matrix in which the elements on the main diagonal are equal to the same non-zero number and all others are equal to 0, we call scalar matrix. Okay, so for example, for a scalar matrix, it's let me here copy and paste so not to do the same thing. Copy, pasting here. Okay, so in this case, scalar is going to look like, let's say, 3, 0, 0, 0, 3, 0, 0, 0, 3. So if on imaginary diagonal line, numbers are the same, then we have scalar matrix. If on in other elements are 0. But if on imaginary diagonal line we have different numbers and the rest of matrix is 0, then we have diagonal matrix. Next is coming identity matrix. Identity matrix, it's same, similar to scalar and diagonal matrix. With the difference is identity. That means on the diagonal line we have all around 0 at the 1. I'm sorry, 0, 1, and the rest is 0. 1, 0, 0, 0, 1, 0, 0, 0, 1. It has to be 1. So it will be called identity matrix. The rest is 0. Only on diagonal we have 1. Okay. Next, let me see what other types are there. Yeah, we have row matrix. Okay, when we have A11, A12, let's say, blah, 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 A1N. For example, it's going to be 1, 2, 3, for example, 4. Row matrix. Column, accordingly. Column matrix, it's going to be A11, A21, A31, blah, 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 AN1. Example, it's going to be 5, 7, 3, 4, another 5. Column matrix. Okay? We already mentioned rectangular, but let's bring example for rectangular matrix. Which one is rectangular? Remember? When the rows and columns are different, not equal. So A11, A12, blah, 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 A1N, and here I have A21, A22, A2N, and I have AM1, AM2, blah, 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 AMN. You see? M and the M, N columns and M rows. So M is not equal N. Let me write down here. So example, I have 4, 5, 6, 7, 3, 2, 1, 0. There, it's rectangular. Lastly, I'll show you upper and lower triangle matrices. Okay? So upper and lower, I'll put upper triangular matrix. Okay, let's say we have 2, 0, 0, 3, 4, 0, 6, 5, and 7. So, well, I showed lower one. Let me write down. Lower. Here is our triangle. Look. See? Okay. And the upper one, upper triangular, matrix is going to be, let's say, 4, 6, 7, 0, 3, 4, and for example 0, 0, 5. Look. This is upper triangular matrix. Okay, let me see. Did I mention everything? Let me go back. Row matrix, I have it, and column matrix, I mentioned it. Rectangular, we have it. Square, I didn't show, but you already know square. We mentioned, I was talking about the square when row and columns are equal amount of rows and columns. Zero matrix, I didn't put here, but on the top I spoke, but let me just put also zero matrix. Okay, 1, 2, 3, 1, 2, 3, 1, 2, 3. Doesn't have to be a square. It can be anything. Diagonal matrix, do I have it? Yes, diagonal. What else was scalar matrix? We have it. A unit matrix. Here it is identity. Let me put here also in parentheses so you will know. This is also we call unit. Just like a unit circle, a unit matrix, a unit vector. So unit meaning 1, size is 1. Okay. I think I covered every single popular type of matrix, and from next video we start doing some operations with matrices. Okie dokie.